graphing exponential, maybe I'll put, these are going to all be our parent functions before we do our transformations. So graphing any parent function that's exponential. So if you're graphing y equals 7 to the x, you're always going to label 0, 1. You're always going to label an asymptote at y equals 0. You're going to label one more point, and that point is when you plug in x equals 1. Well, this is really easy mental math. 7 to the power of 1 is 7. So we'll have the point 1, 7. And with those 2 points and our asymptote, you're going to say, my graph looks like this because I know that this is the basic shape of an exponential function. So what happens when we do that same thing with 1/5 to the x? Again, you're going to plot the point 0, 1. You're going to have an asymptote at y equals 0. And the thing that changes with exponential functions is what happens when you plug in x equals 1. So when I plug in x equals 1, 1/5 to the power of 1 gives me 1, 1/5. And so this exponential function has the same shape, but it's decreasing towards the asymptote. So for exponential functions, they're either increasing or they're decreasing, depending on what the base is. And it depends on what happens when you plug in x equals 1. And so what's going to happen is this will be our parent function with those 2 key points, and then we're going to do our transformations from left to right like we've done in the past in order to graph any exponential function with any additional things. So turn to 1.2, and in 5.2 on page 345, they summarize whenever a is bigger than 1, that's when it increases like this. Whenever a is between 0 and 1, that's where it decreases. But I think with our examples, with actual numbers, again, what did we do? We said we need to look at what the base is, and we're going to label that, in this case, 1, 7 or 1, 1/5. We're always going to draw the point 0, 1. We're always going to draw the asymptote at y equals 0. So when we go to example 1, whoa, let's see the answer already. Quickly erase all that for you. And we want to graph 1/3 to the x. Well, what are we going to do? So set up our axes. We always are going to label the point 0, 1. We're always going to have an asymptote at y equals 0. And then we need to plug one more point in. Well, since when we plug in x equals 1, we're going to get 1, 1/3. And then from that, we have enough information. This is a decreasing exponential function. So the question on part B says, think about things. What happens when you increase x by 1? What happens to the y values? Well, we have 0, 1. And when we went from 0, 1 and increased x to 1, we went to 1, 1/3. If we would do another value, increase x by 1 again, we would get 2, 1/9. What's happening to our y values? When you go from 1, how do you get to 1/3? And when you go from 1/3, how do you get to 1/9? By the same operation. We're multiplying our y values by 1/3. And that's what an exponent does. An exponent is repeated multiplication. So each time you increase your exponent, you're multiplying by another 1/3. Because 1/3 squared means 1/3 times 1/3. And 1/3 cubed means 1/3 times 1/3 times 1/3. And so each time you're increasing and multiplying y by another 1/3. Is this function increasing or decreasing? Since it's going down from left to right, we'll say it's decreasing. Since there's an asymptote at y equals 0, there are no x-intercepts, but we do have a y-intercept. A y-intercept at 1, or you could actually label the point. The y-intercept is 0, 1. We labeled our asymptote on our graph so we can write the equation of it there. It's y equals 0. For our domain of our function, our domain is everything. Our range, our y values are bigger than but not equal to they're just bigger than 0. Of course, you could use interval notation. You could write this as negative infinity to infinity, and you could write this as 0 to infinity. Either are fine. So, some straightforward graphing questions. Try 3, 5, and 7.